Welcome back everyone to the lecture about applied bioimage analysis. This week will be about hypothesis testing, and with that we are entering the field of inferential statistics. So before we can get started with that, I will give you a little introduction to what a normal distribution is. I will introduce you to the central limit theorem. Then we will have a look at hypothesis testing. I will introduce you to a couple of tests you can apply, and then I will show you how this works from Python. So, but before we can get started, we have to think about random variables. So we are measuring something which results from a statistical process like throwing a dice or measuring a property of a cell. And we know that these measurements are surrounded around a given mean, and we know that these measurements are deviating from the mean with a given standard deviation. So this is the link to descriptive statistics we did in the recent weeks. And the normal distribution is characterized by this equation. We are talking about the probability of observing a sample in our population, and this is related to the mean and the standard deviation we measured earlier. And here on the right, you see this typical curve of a probability distribution, how it looks like. And also you have also seen this plot earlier. It tells us something about the probability of an event or of a sample of an observation in relation to the mean and the standard deviation. So you see here, so the mean obviously is the center, and the standard deviation describes, descriptive statistics describes how wide our bell curve is. And inferential statistics is basically built on the fact that a certain number of observations usually lies around the center and just one standard deviation away. This is how the curve is defined, and this is also what we observe when we sample from a normal distribution. So we can say that something like 2/3 of our measurements will happen between minus one standard deviation away from the mean and plus one standard deviation away from the mean. And a lot of theory is built on this assumption. So, and that's where we will go very deep today. There's different distributions, and especially when we want to assume, or when we want to apply tests which assume that our samples are normal distributed, then sometimes you have to apply a test in order to find out, in order to characterize your distribution first. So let's talk about a normal distribution. So this is a random sample I have taken with a little Python script. I will show you later how you can do this yourself. And it looks like a bell curve, right? So from a visual point of view, we can already say, likely that's normal distributed. If we want to quantify that in more detail, if we want to really put a number on this, we could from the left to the right take these little bars. It's a histogram, right? So these the bars of the histogram we sum. So we are basically measuring the area under the curve from the left to the right. So we start here, the area under the curve is 0. Then it becomes higher and higher and higher. So we always kind of measure the area of from the negative infinity until the point where we are, and we write this area, we write in a diagram. This is our blue curve here. So from left to the right, it's increasing until we kind of reach the peak, and then when the probability is decreasing again, we see that the curve here is again is flattening, right? Everybody was recently talking so much about flattening, so here you see it. So when we sum the area from the left to the right in a normal distribution and draw this in a diagram, so the blue curve here, and if we compare it to a given distribution, to the mathematical model, for example, of a normal distribution, that would be the red curve, we can in such a plot, in such a diagram, measure the distance between these two curves, and this tells us in a number how close my distribution, my observed distribution, is to a given distribution. The name of this test is the Kolmogorov-Smirnov test, and it maybe sounds complicated, but at the end it's a function you call from Python, and you can just apply it. As for other distributions, so for example, the uniform distribution means that you have a certain range of values where you can pick from, and they are all equal distributed, they are uniform distributed, so the likelihood of happening any value there is the same. Unlike in a normal distribution where the values, where the likelihood, the probability is denser close to a given mean. Furthermore, what we observe in nature quite often, especially when we talk about image analysis and image processing, a bimodal distribution, for example, you have an image, half of the image is black, the other half is white because there are cells, so there is something and there is some gray in between. If you now look at the histogram of this image, you are looking in the most cases, in many cases, at bimodal distributions, cells, no cells, right, mixed in one histogram. And depending on how close these gray values to each other are, it might be easier or not so easy to differentiate them. So a bimodal distribution like this one, now think of the O2 algorithm for thresholding, it would likely find the threshold down here. If you think a bimodal distribution like this one, I'm not sure if O2 would have an easy time of finding a good threshold here to differentiate these two things which are there in our distribution. Just a little reminder of what thresholding algorithms do with gray value distributions in images. So that brings us to the central limit theorem. When sampling from a distribution and we have independent observations, this is kind of decisive here in this case. It's not like there's a bowl with balls of different colors and at some point there are no red balls left and we can only pull a blue one. An independent observation means I go out on the street and I measure the height of a person and then I measure the height of the next person, and it's not like that the people who are 2 meters high, there are no people left anymore. It's like the height of people is an independent variable. And if we sample from such a distribution, for example, a population of people out there on the street, we can assume that the more people we measure, the more samples we derive from our population, that it will go towards a given, so the mean of the samples we have will go towards the mean of the population anyway at some point. So let's start with one sample. So I have here one sample of normal distributed numbers, and it's this one sample was something like minus 0.3. And I continue sampling, and now I have 5 samples, and I still look at the histogram, and it's like when you look at this distribution, and it's like we have sampled from a normal distribution, so it does not look like a normal distribution yet, right? Because we don't have enough samples yet. But the more samples I get at some point, it starts looking like a normal distribution. Maybe not at 10, but maybe at 50 or 100. So, and this is so the central limit theorem is kind of the basis of inferential statistics. At some point, it depends on the problem we have. It depends on what we are looking at. But if we continue sampling and have more and more measurements, at some point it will look closer and closer like a normal distribution. Also, if we sample a small sample from our population, which is normal distributed, then analyzing the distribution of this small sample brings us something if we know that the population is normal distributed. So the central limit theory basically allows us to draw conclusions from samples about the population. This is inferential statistics. This is what we want to do, right? We want to learn something about our population by sampling from it. And this is also a nice way, there's also a nice way to look at something we discussed 2 weeks ago. We had an issue with understanding our box plots. So when we look at our box plots, so we have two box plots, each with one value sampled from a random distribution, from a normal distributed random numbers. And if we look at these two numbers, if we draw a box plot of these two numbers, we basically just see the little orange line, meaning the median, which is the value we sampled. But if we continue sampling, the box plots do not fit to what is written in the documentation. So we read in the documentation, so that was in one of our meetings, we read that this bar here between the box and the whiskers should actually be 1.5 times the height of the box. So we were a bit confused about that, and that's why I was programming this little simulation here. When we continue increasing the sample size, so now we have 5 samples, and we continue to 10, and we continue to 20, and we continue to 50. These two, we are looking at two random samples on the left and on the right. And if we continue increasing the sample size, the same thing like what I just showed in the histogram of the distribution happens. These two samples look more and more like a normal distribution because the number of samples is becoming higher and higher, and we are sampling from a population which is normal distributed. And at some point, indeed, the height of these lines here corresponds to 1.5 times the box height. So The issue we had 2 weeks ago when we were discussing the box plot was just that there's not enough, we did not derive enough measurements to see a box plot in how it's supposed to be. If we continue sampling from our normal distributed population, these two samples become closer and closer and visually in this plot. And this is what we expect because of the central limit theorem. And this is what we exploit when doing inferential statistics in order to conclude about the population. So there is two terms. I mix them up all the time. I'm super sorry about that, but in German it's the same word. Probability and likelihood. So probability is the chance of observing an event from inside the population. The likelihood is the observed value or event in one particular sample set. So the one thing is a theoretical one. The population gives us a certain probability. The population has properties. One of these properties is the probability of an event happening in this population. So for example, the probability of finding a person which is 1 meter and 80 centimeter high. So there's a certain probability associated to that. If I now go out and measure the height of 10 people, I actually can draw a distribution, a diagram of the likelihood, what I observed. So the one thing is a property of the population, and the other thing is a property of the observation. To make a long story short, let's think about the probability in a population of grades in an exam. So this is one of the classical examples. So usually, depends a bit on the lecturer, and also depends on the students, but usually we have a normal distribution, a Gaussian distribution of grades in exams. So for example, here in this case, you see that the grades are normal distributed around, I think, 2.5 or something like that. And you see that there is a certain distribution of grades in the exam. We can now this is information we have about the population. So this is kind of in general true because we know for long-term study, we know this kind of property. We can now from this distribution, we can conclude that the chance of a student not passing the exam is something like 10%. So according to the German grading system, you do not pass the exam if you get a mark 5 or 6. So the chance of getting a mark 5 or 6 is something like 10%. That also means that the chance of a student passing the exam is 0.9, it's 90%. If I now take 2 students and want to measure that these 2 students pass the exam, the likelihood of this event happening, so I take 2 students out of the class and I want to know the likelihood that they both pass the exam, the probability goes down. The probability of this event happening, that both students pass, goes down because for each of them, the chance of passing the exam is just 0.9. And you can continue this experiment, this Gedanken experiment. With 5 students, the probability of all 5 passing the exam is just 0.59, so something like 60%, and so on and so on. And it brings us to a point where the chance of 60% of 60 students, so that's all students in the class, passing the exam is just 0.0018. So don't be afraid. The point here is likelihood, yeah. So the likelihood comes from a population of independent samples. So it's not that at some point all the marks 1, 2, 3, 4 are out and you now have to get a mark 5. No, every student is independent in getting a mark. And that's why we can actually calculate the probability of all students passing the exam. And it's just something like 0.2%. Again, on the left side, we have the population, and we have in the population, we observe a probability. And we have on the right side, we have a sample, one group of observations, where we have to talk about the likelihood. Furthermore, this value I calculated here, the probability value of observing this sample when sampling from the population shown on the left, is the so-called p-value. We will come back to this one. It's just here now I tell you that it has something to do with the chance of sampling this sample set or a sample set with these properties from our population. So it is very unlikely that we get this sample from our population. This is what the p-value tells us if the p-value is so small, right? One last thing about this, so exam grades are no random variables. You do have influence on your grade, just saying. So hypothesis testing, we almost did it already. So when putting lectures online, we are now performing an experiment. We performed an experiment, or we are still performing it, and we want to report about this experiment. So hypothesis testing now in the context works like this. Assume we observed this distribution as I just showed on the slide before. So all students passed the exam, and we were thinking about, okay, what did we do different this year? This year, all students were taught online. So we had online teaching and no in-house teaching anymore. So, and that's why we can write something like, when putting the lectures online, significantly more students were passing the exam. So this is, we describe our observation. We did something, and then we observed something else. So we observed that all the students passed the exam, and we have a p-value describing our observation. So, and we will go a little bit more deeper into what's significant and what the p-value means. But for now, let's first of all think about what it does not mean. So it does not mean that all students will pass the exam because the lectures are on YouTube. So we cannot conclude that. We have to be very careful with generalizations. We cannot conclude that this will for sure happen because we don't know. We just can talk about our sample. And that's what the statement rather says. We observed differences and we assume that these differences are related to what we did differently. We did e-learning. We did not go into a lecture hall. And we assume that this is related to all students passing the exam. So we cannot do online teaching with the whole population and then figure out if they all would pass the exam. And we cannot repeat the same semester with the students from last year and see if their grades are improving, because their grades may be improving anyway because they learned the same thing the second time. So in order to learn something about online teaching, is it good or is it not good, we have to sample, we have to get an independent sample, so this is you now, and we have to apply hypothesis testing. This is why we are doing all this. And this is basically how it's done step by step. So in hypothesis testing, we do the following. For example, first of all, we know that the mean exam grade over many years, over many students' sample sets, we know something about the population, and we know about the population that the exam grade usually is 2.5. When teaching online, that's what we did this year, we observed the mean exam grade was 2.3, I hope so, or even better. And we applied a t-test, this is what I will show you next, to determine if these observed differences were significant. So we first of all describe our population, then we describe our sample, then we describe the method, the statistical method we apply in order to learn something. You can, for example, find all these tests online. On Wikipedia, there is a very detailed description of for example, the student's t-test. And you find usually in the documentation of the Python libraries, for example, you are using, you find these sentences describing what the test actually does. And it is always a bit technical and it sounds a bit weird, but that's why we are here today. And that's why we go through this together at least once. So the t-test for one sample is a two-sided test for the null hypothesis that an expected value mean of a sample, so this is the mean of the sample we observed, is equal to a given population mean. So we compare the mean of the population and we compare the mean of the sample we just derived. And this test is able to tell us that these two values are the same. But if you think back, we do not want to show that A and B are the same. We do not want to show that the students have the same grade. We want to show that the students have a different grade because online teaching was improving teaching. This is the thing with hypothesis testing. You have to wrap around your mind. We have to conclude in a different direction. And I will go a little bit deeper into this here on this slide. What we are investigating, what we want to show is students had a significantly different grade when learning online. So this is our starting point. We want to show that something's different, that the means are different. That's our starting point, and the starting point is called alternative hypothesis. The opposite of the alternative hypothesis is that students had similar grades when learning online. And that's the so-called null hypothesis. if the null hypothesis is rejected, if we can show that this is not true or that this is very unlikely, it is very unlikely that the students had similar grades when learning online. When we can show that this is not true, that this is unlikely, then the alternative hypothesis must be true. The students must have different grades then. This is a bit the order how we go through this. So start from the alternative hypothesis. This is what we would like to show, and then we have to think about how is the negation of that? How is there a right causal relation to a null hypothesis which we can work on? And the null hypothesis actually should be something we can falsify, where we can show that it is not true. And this is again, I was talking about it a couple of times during this semester. Falsification. We must fail in order to learn something, and we flip our question from the question we actually would like to answer. We are not talking too much about it. We are rather finding a different question, fail in that, and while failing in answering this question, or while this question is falsified, answered with no, we learn something about the original question. So that's decisive that these two questions are related to each other, the null hypothesis and the alternate hypothesis. But this is how statistical inference, inferential statistics, this is how it works. So let's first talk about the t-test. So the t-test allows us, that's according to the website, to test if the mean of our observed sample and the mean of the population are actually the same, right? So this is the null hypothesis we can, with this test, falsify. And so this is our likelihood, the probability distribution we observed when grading students after the exam. And first of all, we apply descriptive statistics to it. So we had 60 samples. The mean grade of them was 2.3. There was a standard deviation of 0.5. We have our alternate hypothesis. We think that the grades the students got in this year is different from 2.5. That means our null hypothesis is that the mean of these students, the mean grade of these students is 2.5. Furthermore, we have to define a so-called confidence level. So how sure do we want to be about that? So for example, we are fine if something like the likelihood that we are right is 95%. So we have still an error probability or something like that of 0.05, that's 5%. So that's what the confidence level says. And then we take all the parameters we derived from our sample set and we calculate the t-score. And with the t-score, we look into a table to determine the p-value. And if the p-value is smaller than our confidence level, then we know that our null hypothesis was wrong. The probability of the null hypothesis being right is less than our confidence level. So this is basically the idea here. We show that our null hypothesis, the mean of these students, is 2.5. The likelihood, the probability of that is super small. It is less than 5%, and that's why we can actually reject the null hypothesis. And when we say the null hypothesis is not true, we don't believe it because the likelihood is so small, then the alternate hypothesis must be right. This is the trick. This is what we do when we try to conclude from observations about the population. So this is the trick we are doing. And when you look here at this equation, when you look at this table, you may think, oh my God, it's complicated. At the end, it's not, because you call a Python function which just calculates the p-value for you. Oh yeah, and this equation depends on which test you are executing, and you always find these equations in the documentation of the respective test. So when we think a little bit more about the p-value, we can also do a little experiment. You usually don't see that, and I think it's also in a realistic setup when we investigate data, this kind of looking into the data is not so legal, but for academic purposes, I thought it might be a good idea to show a bit it like that. So assume I was taking two samples from a normal distribution, and you see here on the left, you see my histogram of these two samples. And I want to know how the p-value is dependent on what mean I assume. So these two samples. have a mean for sure, but we are not sure if this mean of these two is related to the mean of the population where they come from. So if we assume that the mean of these two, something like 7 or 6.5, is the population mean, then we can ask with a statistical test how high is the probability that my 6.5, the mean I assume is in the population, is actually, according to the sample, is actually true. So how high is the p-value of my suspected mean of the population, 6.5, when I have this sample distribution? And I can plot this over the suspected mean. So when I observe something like these two values, it is likelier, it is more likely that the population from which I sampled from has a mean of something like 6.5 than 10. I will now increase the number of samples I derive. And with more samples I derive from my population, I also know more about my population. And this is why this curve here becomes tighter. The more samples I get from my population, think of the central limit theorem. The more I sample, the more my sample distribution goes towards the distribution of the population. And the more I sample, the more I know about my population. So if I have more samples, I can with a higher precision tell where the mean of these samples actually is. And that also means that the probability value of the sample of my population being 9 or 10 goes down. And I can continue this sampling, I think, until 1000, and you see this becomes tighter and tighter. So it's actually, there's no edge here, it just has something to do with the resolution I was plotting with. But this is how you should interpret the p-value. The p-value tells us something about if a certain mean we give to the test of the t-test, for example, is really the mean of the population where we sampled from. So it's not the mean of the sample, it's the mean of the population where we sampled from. So there's different tests we can use, and there's really many about them. Many of them I can just show you a handful to explain you how it in principle works. If you later during your master thesis, for example, come to the point where you have to do a certain investigation and you want to know which test is good for that, you have to read more anyway to figure out which is the right test for doing your particular science. But I can show you a handful, and I can also tell you some scenarios where these tests are useful. So for example, if you want to figure out if the mean of a distribution of a sample is significantly different from a population mean, from a given mean, we use the one sample t-test. So this is the classical t-test. Maybe you heard about it earlier. So we have some samples, we have an assumption, we have a null hypothesis that the mean of these samples is 9, and we can apply this test in order to find out if our observation is true. So the null hypothesis is the mean is 9, and we can use this test to show significant differences from 9. What we need for that, we need a sample from a normal distributed population, and we need a given mean. There's the so-called two-sample t-test, where we have two distributions, potentially samples taken from the same population, and we now would like to know if they are different from each other. So this is basically the goal we have. So that means that the null hypothesis is, we assume that the mean of these two distributions is the same. And in order to apply that, we need two samples from a normal distributed population. And then there is a so-called the paired t-test for two samples. So these are not independent distributions, these are related distributions. That makes, for example, sense if we apply two different methods for measuring the same. So that brings us back to last week where we did method comparison. We are measuring with two different methods, so that gives us paired data. And basically the question is very similar to the question before, but we do not check if the mean of two distributions is the same. We rather measure if the mean difference between them is 0. So this is kind of a special case of the situation before. So the null hypothesis is that they are 0. And we can show with this test if there is a significant difference between two methods. So this is what we use this test for, and what we again need is paired samples this time of a normal distribution. And the opposite of that, if we want to show that, for example, it's especially for method comparison, this one plays an important role. If we show that there is no significant difference between two tests, we have to turn the test around, and this is a little bit more complicated here in this situation. It's so-called equivalence testing. So we turn the question towards, we are not, the denial hypothesis is not anymore if it's the same. Denial hypothesis now is it's different. And if it's not different, it must be the same. So the alternative hypothesis is that our two methods do the same. If we want to show the equivalence of two methods, we have to apply an equivalence test, which is under the hood actually two t-tests. So technically also not complicated at all. There's a bunch of statistical tests out there you can apply to your data to figure out if things are different or if things are the same, or if two samples come from the same distribution and so on. And I cannot go through all of them, but I can provide some more links where you can read them. So there's a nice cheat sheet also with some Python code for various tests. There's a Wikipedia page explaining the strategy again. Back in the days, it took me some time to understand what a p-value is and what the confidence level is and so on. And there is a very nice collection of videos in the khanacademy.org. So maybe again, it helps if somebody else is explaining the same thing with different words. Then you can have another additional look over there. So the next will be hypothesis testing in Python. See you soon.